Good morning, everyone. Thanks for joining our webinar today on the topic of NFPA 79 and 70E, importance of electrical safety in industrial control panels. Please use the webinar dashboard and type in your questions as you go through the webinar, and we will answer them at the end. Without further delay, I will turn it over to John.
Good day to you. I'm John Kolak, the president of Praxis Corporation, and I'll be one of your instructors today covering a subject called industrial control panels in the workplace. My part of the presentation will be to focus on the safety aspects of the discussion. After I complete my part of the presentation, I'll hand it over to Banu, who will be talking to you about some updates to some other national consensus standards that apply. Before launching into my presentation, I'd like to give you my background so you have a frame of reference from where I'm coming, and then I'll launch into my part of the presentation. In terms of my background, I began in the electrical world as a journeyman lineman. I actually climbed poles for 13 years before going back to school. I took bachelor's degrees in electrical engineering and a master's degree in occupational safety, and I became a certified safety professional. All total, I have 41 years of experience in the industry. What I'm going to be talking about is on the slide in front of us. We'll begin with some important definitions that will lay some groundwork for you to understand the rest of the presentation. Of course, we're focusing primarily on electrical hazard recognition and control. So we'll be talking a little bit about ICP and lockout tagout requirements. And we'll also be talking a little bit directly from the National Electrical Code Article 409, which is on industrial control panels. We'll discuss the various components that are typically included in ICP panels, but it must be stated at this point that there are so many different configurations, literally hundreds of different ways of configuring these panels. We'll only be able to speak generically about them here, and then you'll be able to extrapolate that to the various units you have in your plant itself. And of course, you can take advantage of the Q&A box in the software to list your questions in real time, and as they come up, we'll try and answer them either in real time or at the end of the presentation. We'll be talking a bit about bonding and grounding, a very important subject in electrical safety, particularly important in this particular type of equipment. So we will discuss that briefly with the understanding that there's going to be a lot more to know about that than what we'll cover in this presentation. And I'll close my part of the presentation with a little bit of discussion of maintenance of ICP components taken from the NFPA 70B. Let's go to the next slide. There are a few definitions that we need to understand before we press forward with the presentation. The first definition is called short circuit current rating. Now we need to differentiate the short circuit current rating from the interrupting rating of a protective device, in that the short circuit current rating takes into account all of the equipment in the panel, not just the overcurrent device that protects the panel itself. So this is an important definition to keep in mind because we have to size the equipment appropriately to handle the weakest element in the system. Bonding and grounding we'll discuss together in the sense that the purpose of bonding is to equalize voltage between conductive parts on the frame of a piece of equipment, in this case the covers for the panel itself. So we bond things together to equalize voltage so we couldn't touch two different surfaces and have a voltage between them. Grounding then is we take that same bonding connection and connect it to planet Earth in the vicinity of the work location. So the purpose of bonding is to equalize voltage. The purpose of grounding is to put the panel at ground potential in the vicinity of the work location. We need to also differentiate between neutral conductors and what we call equipment grounding conductors, abbreviated EGC. Now, equipment grounding conductors are the same as the third prong on the outlet on a plug on an extension cord. And the purpose of the EGC is to make sure that if that equipment has an internal fault, that it will quickly trip the system offline so that it doesn't harm human beings working on or with that equipment. Neutral conductors, the difference between them is a neutral conductor is a purposeful current-carrying conductor. We engineer it and install it with the intent of it carrying amperes of current in the system. Conversely, the equipment grounds actually normally have zero current on them. The only time they have current on them is when there's a ground fault, typically in the system. Now, the key point I want you to get from this discussion is that there could be a voltage or a difference of potential between the neutrals and the equipment grounds. if the bonding and grounding back at the panel itself, the source panel, is not properly connected. So it's very important you understand that if the connections are not appropriate at the source, there could be a voltage between the neutral conductors and the equipment grounds on the same piece of equipment. Last but not least, a lockout-tagout term is called an energy isolating device. We need to be able to differentiate EIDs from control circuitry. Under lockout-tagout, it would be illegal to lock out a control circuit. We can only lock out, tag out EIDs. And so we'll go through pictures of the various panels we're talking about here today, and I'll outline where the EIDs are and where the control circuits are. So let's go to the next slide. In terms of what actually is an industrial control panel or what it includes, this can be found in section 409.2 of the National Electrical Code. Now, as you can see by looking at the words on the slide, it's an assembly of two or more components. Almost always it includes both a power circuit and a control circuit. Now, under the power circuit umbrella, we are talking primarily about things like motor controllers and overload relays and fuse disconnects and the like. These are the things that actually provide power to the actual equipment, as the name suggests. In the control circuit side of the cabinet, this is usually the selector switches and time delay switches or relays and control relays. This is sort of the brains of the outfit. This controls the power part of the system and runs things like programmable logic controllers and other devices that are smart things in the system. And it usually does. It is a combination of the two in almost all cases. These components are mounted in the enclosure with the wiring and terminals in it. And the industrial panel actually does not include the equipment that it's controlling. So again, this is the focus of our presentation, and usually it has both power circuitry and control circuitry. Let's go to the next slide. Let's talk a little bit about electrical hazard recognition and control. Now, the big three hazards we manage anytime we're talking about electrical systems are electrical shocks, electrical arcs, and electrical blasts. Now, electrical shocks happen anytime electrical current measured in amperes flows through the human body. And as it turns out, we don't need a lot of current flow to kill us. 50 thousandths of 1 ampere actually would be enough to precipitate electrocution in most situations. So one thing that we can take for sure is that industrial control panels almost always have electrical shock hazards. In fact, the data you can see on the slide here is that there are 70 fatalities, electrocutions, each year on industrial control panels on the job. So I think sometimes the small wires you see in these enclosures may lead one to believe there are no hazards there, and there almost always is an electrical shock hazard associated with industrial control panels. Having said that, electrical arcs and electrical blasts have a lot to do with the capacity of the system, and in this case, those small wires does matter. So on this particular panel, there is not a significant arc flash hazard, except for if you look at the picture in the very bottom center of the picture, where you'll see three colors, yellow, green, and purple there. Those conductors coming into the panel might have enough capacity to precipitate a significant arc flash. The arc flash that you see here is the one that I would expect in an industrial control panel, in that it could be harmful to your hands or your eyes, but it would not normally precipitate the kind of arc flash we're trying to manage with the arc-rated clothing and things that we wear on the job. So in other words, it's going to be up to the worker doing the work to ascertain the shock hazards and the arc flash and arc blast hazards in the workplace. So let's go to the next slide. Now, what we see in front of you is an example of a industrial control panel. Now, let's be clear, there are literally hundreds of different configurations for industrial control panels. So this is by no means the standard by which we should measure them. This just happens to have a lot of the equipment we'll typically find on both the AC voltage side and the DC voltage side of the panel. And we'll go through each section of the panel and talk about the electrical hazards associated with each one. But as you see the way the overview of the panel is depicted in front of you, the top tier of the cabinet is actually the incoming power circuitry. Both the AC and DC power is in that tier of the panel. The middle panel is actually the brains of the outfit. This includes a programmable logic controller and some of the Ethernet connections and radio connections in the panel. And the bottom tier is actually the terminal blocks, where all of this control power is directed to the actual equipment that it controls. So let's go to the next slide and we'll break down each one in a bit more detail. Okay, let's talk about the incoming power side of the industrial control panel. Now you'll see there's a red arrow under the main circuit breaker. The arrow is pointing at the only energy isolating device in the whole enclosure, and that is the main circuit breaker. So if you were going to lock out this panel for whatever reason, that would be your lockout point, the EID in the system. Now let's be clear on something. This particular panel just has 120 volt single phase power coming into the panel. And that's the reason for the single breaker that you see. Now I've got on that arrow under the main circuit breaker, it's pointing to the incoming side of that breaker. It is very common to have three-phase 480 volt power on the source side of that breaker. And in fact, it can be high enough capacity that it could precipitate a significant arc flash. Further, there's often a transformer there where the 480 volts would be stepped down to 120 volts. And that then would be what you'd see coming into this panel. So it's possible that you could have, instead of a single circuit breaker, have a transformer that has high enough capacity to precipitate arc flash hazards. Moving to the right, in this on the top tier here, we see the AC incoming power to the system. You'll see AC power and a red arrow pointing at a terminal block that actually consists of all, or contains all of the AC circuit breakers for this particular panel. Moving to the right of that, you'll see the neutral and grounding bus. The neutral bus with the white wires are connected together, and the green wires represent the grounding bus. Taken as a whole, from the grounding bus all the way to the circuit breaker on the left side, this is the alternating current side of the switchgear, of the control panel. Now again, this represents very legitimate shock hazards. I would recommend wearing rubber gloves if you're doing voltage testing or whatever on this side of the enclosure. And it also represents very low arc hazards on this particular system. With that said, if that incoming source was 480 volts, three-phase, that would all be, this would all change. There could be very significant arc flash hazards in the panel. It's just this particular one does not represent significant arc hazards. Moving to the right, you'll see the DC power source. This acts as both a transformer and a rectifier. What it does is it converts the 120 volts down to 24 volt DC power, and immediately to the right of that are the circuit breakers and the grounding bus, and the equipment grounding bus for the DC side of the panel. The DC side represents very little shock or arc flash hazards in this particular panel, but once again, the qualified worker requirements will stipulate that they must be trained to recognize where the hazards are significant and where they aren't. And in this particular panel, it's fairly low arc flash hazards, but significant shock hazards on the AC side of the panel. Let's go to the next slide. On the middle tier of the cabinet, we have the brains of the outfit, if you will. The first thing you see in the middle of the panel is the programmable logic controller in this particular unit. And again, there can be many different kinds of devices, variable speed drives or whatever, can all be included in this panel. This just happens to be the PLC part of the panel. To the left of the PLC, you'll see the Ethernet switch. This is used where we're connecting, say, Cat5 cable to it to actually allow this system to talk to a different system. And then in the far right side is, in this case, a radio connection, which allows for wireless communication between this part of the panel and other types of equipment as well. And you'll see there's some various ports, Ethernet ports, and so on the radio equipment in the panel as well. So let's go to the next slide. And let's look at the bottom tier of the industrial control panel. This includes the terminal blocks and the relays for the panel itself. On the left side of the terminal blocks, you'll see TBA is the listening terminal block analog. So the analog signals are on this part of the cabinet. This would be things that control things like flow levels and so on. In other words, analog data. In the middle tier here, we have the TBD, which is the digital part of the panel. So the digital, of course, is more the on-off part of the system, so it controls things like switches. And on the far right side are the relays for the panel itself, and these can be everything from motor starting relays to whatever it is that we're controlling with the panel itself. So this is where all of the controlled AC and DC systems, in this case the DC systems, come together, and they're distributed out to the equipment that is controlled by the industrial control panel. So let's go to the next slide. Article 409 has some marking requirements that are noteworthy. Of course, it needs to have the manufacturer's name and trademark on it. This is very important because OSHA generally defers to the manufacturer on everything from required maintenance procedures to lockout tagout on systems. So the manufacturer's name is important to have on the gear. The equipment ratings are what you see in yellow, identifying the actual supply voltage. And if there's a transformer associated with it, there'll be a high side voltage and a low side voltage on that transformer. Whether it's single or three phase is important. The frequency of the system, 50 or 60 hertz, or if it's direct current, of course, there is no frequency, and full load current on the equipment as well. Those are just some of the markings that are expected to be on there with respect to equipment ratings. The short circuit current rating also needs to be on here, which we discussed in the definitions section. If it's going to be used, as we said, for service equipment, it needs to be so marked and for that kind of duty. And then finally, the electrical wiring diagram reference. It is an OSHA requirement that all fixed facilities have accurate schematic diagrams of the facility. And so this should show up on a schematic diagram that not only has a diagram of how it fits into the overall system in the plant, but also the internal wiring of this piece of equipment as well. So let's go to the next slide. Let's take a look at the maintenance requirements of industrial control panels as outlined by the NFPA 70B. Now, of course, I'm just going to hit the high points here in this discussion. You would, of course, want to do a full reading of this if this applies to you in your operation. The first point they're going to make is that other than just visual inspections, they believe that parts should be removed from service in order to effectively perform maintenance on them. Now, again, that's up to you in your operation as to whether that's relevant to you, but that's their suggestion. The second point will be that control modules should be of the plug-in type if possible. This is not only for expeditiously changing them out of service, but also for safety. The next section talks about the idea of fully compartmentalized for safety. And what they're saying here is that we use compartmentalization to isolate the dangerous parts of the equipment from the not so dangerous parts of the equipment if possible. Other electrical regulations use the term effective isolation for the same concept. And this is, of course, a design change. We design and build the panel with that thought in mind. Power supplies need to be checked for what you see in yellow here on the slide. The voltage level changes. This presupposes that we know what the normal voltage levels are of the equipment. And if they've changed, and we can't attribute it to something obvious, like a change in voltage from the utility, then of course we'd want to figure out what's going on. That may be indicating that the system is beginning to fail. Ground faults in the system, of course, need to be identified and isolated. An important thing to consider with ground faults is depending upon the impedance or the resistance of the fault, it is possible for a ground fault to develop and it will not actually trip the system out of service. In those situations, you can have an ongoing shock hazard where a piece of equipment, the frame of a piece of equipment gets energized and stays that way. And of course, those things need to be cleared immediately in the system. The integrity of the trip circuits also needs to be checked and verified and maintained to make sure that if there is a trip in the system, that it expeditiously trips the system out of service. Current carrying parts need to be maintained both in terms of continuity for making sure the connections are not oxidized or whatever, and that they are properly connected and tightened down in place, making sure they exist for that, and also for if they've been exposed to overcurrent or over voltage situations where it becomes apparent that they got hot or there's flashover of the insulators, and any of those flashover of the insulators would render the system in need of replacement parts. And finally, if there's environmental damage to the equipment, again, this can be corrosion, but it can happen from just the environment that you're in. For example, if you're in a highly corrosive or a salty environment near a coast, or it could also be from solvents that are used in the vicinity of the equipment. And in terms of the intervals for inspection, well, that's going to be driven by need. If there are safety implications, for example, circuit breakers that have been reset frequently, or reliability considerations, or the severity of service. In other words, if they've been subjected to current flows at or near their limits, the intervals may need to be shortened up or tightened up, and the maintenance may be more aggressive. So let's go to the next slide. I have just a few thoughts that I'd offer before I go ahead and turn the presentation over to Banu. First of all, because there are so many different ways of configuring them, an industrial control panel, I encourage you to have a rigorous hazard assessment as part of the job briefing discussions before work commences. Now, every qualified electrical worker is required to be able to do a basic hazard assessment, namely a shock hazard analysis and then an arc flash hazard analysis as well. This is so because especially in situations when you're troubleshooting, a piece of equipment may have failed catastrophically inside the panel or inside the piece of equipment, and the normal switching procedures would no longer apply. In those situations, the qualified electrical worker will have to come up with what we call a special precautionary technique, and they will come up with an alternative system of achieving equivalent protection in that situation. I recommend that you have that kind of discussion when working on industrial control panels because each one could be quite different from the other ones, even in the same part of the plant. The second point is that you can assume that industrial control panels present a legitimate shock hazard. This is especially true on the AC side of the equipment, but even on the DC side of the equipment when it's in the 120 volt range is also worth managing. Some, not all, may have arc flash hazards as well, especially when the source is an incoming three-phase 480 volt system that steps it down to like 120 volts. Those kinds of sources often can produce arc flash hazards that need to be assessed and managed. And finally, I think just the small size of the equipment could tempt us to become complacent when working on these panels. I encourage us to fight that urge to remain vigilant and even exceed minimum requirements, such as possibly wearing your low voltage gloves when working on the AC side of the equipment especially. So with that, I'll go ahead and hand it over to Banu. God bless.
Thanks, John, for such a great information and providing insights into industrial control panels, specifically the types of electrical hazards involved, and also the importance of short circuit current ratings and other maintenance aspects of the control panels as well. By the way, my name is Bhanu Srila and I have an electrical engineering background similar to John. I had spent about 20 years in power generation and distribution industry. I primarily worked in the design and development of large size power generators for standby and prime applications. I've been intimately involved with NFPA 70E and 70B standards for electrical safety and maintenance practices in my last 4 years since I started working for Grace. Also, I'm a certified electrical safety compliance professional from NFPA, and further I sit on the standard technicals panel for UL 508A, UL 1436, UL 61010, and also 60947-4. Today, I will be touching on the NEC, NFPA 79, and UL 508A correlation, and also discuss about the safety specific concerns as we deal with this equipment as well. Finally, I will also provide few updates on the NFPA 79 with the 2018 edition changes, and we'll take the questions at the end. As most of you know, NEC is deemed to be the overriding code for the installations in the United States, and again, it's legally recognized as state of the art. Strict adherence to NEC is mandatory as the equipment cannot be put in service in the states without the approval of authorities having jurisdiction, also called AHJs. Article 670 in NEC refers specifically to industrial machinery requirements, which in turn refers to NFPA 79 for additional information and clarification needs. Further, Article 409 in NEC refers to industrial control panels codes, which references UL 508A standards. NFPA 79 dates back to 1960 with about 13 revisions since then, and the 2018 edition was released in November 2017. UL 508A, on the other hand, is currently in its third edition that was released in April 2018. We'll talk about these more in detail in our next slides. Let's go to the next slide. Let's take a quick look at NFPA 79 and UL 508A in terms of what is covered and what's not covered in the scope. So basically, electrical and electronic equipment with a nominal system voltage of maximum 1000 volts are covered in both the standards. Okay. The next one is point of connection to the machine. So here we're not talking about connecting equipment to a service feeder or a commercial utility as well. So we're talking about basically a machinery connecting to the supply side of the conductors. Okay. And then both the standards address safety for the people and property. So safety for the people in terms of protection against arc flash and shock hazards. And in terms of property, it's the damage to the equipment itself. And then the next bullet is hazardous area equipment is not covered in the standards. Okay, so hazardous area is covered in NFPA 499 standards. Okay, and the last bullet here is it does not apply retroactively, meaning you don't have to comply with every new version of the standard as it's get released after the equipment is installed and put in service. However, it must be applied when you make specific changes to those existing machinery as well. You can just exempt repairs from that equation. Okay. So because both the machine supply and control panel supply generally involve same supply terminals, right? It's also possible both standards apply to the control panels. So whenever in doubt, make sure you agree with in advance with the end user which standards is relevant to them. In practice, however, this cannot always be clarified beforehand. In this case, it's almost always recommended to comply with both the standards. This does not pose a major problem because two standards are not contradictory and most requirements are somewhat similar or identical. In some cases, one standard allows less room for interpretation of requirements than the other one. In this case, it's always recommended to comply with the more stringent requirement. So for example, if you take NFPA 79, you can use the 120 volts AC or a 250 volts DC for control circuits. However, in UL 508A, a maximum 600 volts applies to class 1 control circuits. So in this case, it's always good to follow the more stringent one, which is NFPA 79 in this case. And again, voltages according to 79 are also acceptable if you look at it according to UL 508A as well. Let's go to the next slide. This slide shows a quick graphical representation of the application of these three codes and standards what we discussed. So first thing, all the equipment, machinery, panels, and the connections to this equipment in the solid white area has to adhere to the NEC installation code requirement or NFPA 70. Okay. The next one is the shaded red area show the industrial machinery space which has to follow NFPA 79 machinery standards. Okay. And the last one, the solid red area, which is shows the industrial control panels within the machinery area has to comply with UL 508A standards. Okay. Let's go to the next slide. Let's take a look at the changes to NFPA 79 2018 edition. Okay. So the first and foremost thing, code harmonization led to drive consistency between NFPA 79 and UL 508A standards. Okay. The new revision of 79 is updated to be consistent with the current UL 508A voltage classification tables, which defines up to 1000 volts and over 1000 volts from the previously defined 600 volts classifications. So if you see in 2018-79, all the voltage classifications are called out in 1000 volts nominal voltage range. The next one is section 4.3 that was added to 79, which states listed and labeled equipment shall be used in accordance to manufacturer's recommended guidelines. This is again an exact alignment with the NFPA 70E and 70B standards as it was published in 2018 and 2019 editions. Okay. The next bullet here addresses about special cable requirements for flexible motor supply that protect the cables against damages in non-linear load applications. So primarily this is for variable frequency drives to overcome the damages to the cable itself. So this is called out in 442.8, which is a new requirement too. And the last one is a 7.8.1, which requires surge protection devices, or they call SPDs, for safety interlock circuits. Okay, these are some of the changes that came into play in 2018 revision cycle. Let's go to the next slide. So this slide shows some of the changes addressed in Chapter 5 in NFPA 79 for disconnecting means. First things first, machine is considered an individual unit in the context for NEC, and so it must be supplied with a disconnecting means, period. All the terminology around the supply side conductors has been changed to machine side supply conductors. which brings the clarity. It is not a supply conductors on anything. It's basically referring specifically to call it out as a machine side supply conductors. And then throughout the text, the term incoming supply circuit is replaced with machine supply circuit, again to be consistent and be specific in the terminology. And the next point is the disconnect means can be integral to the machine, or it can be separate within the line of sight, and also it's readily accessible and is marked in accordance with 53111. Okay, and the next one is there's no need for the overcurrent protection for the disconnect, similar to NEC 670.4, but it must have a circuit breaker or the fuses in the upstream. Okay, so where practical, a machine must have only single power supply source, and the disconnect must always isolate the electrical equipment from the supply itself. Okay. Also note that the communication circuits are not required to be provided with the supply side disconnecting means. One, it is not necessary, and two, it's not even practical to include disconnecting means for limited energy circuits as defined in Article 724 and 800 as called out in NEC reference. Okay. Also make sure if the machine's main disconnecting means supplies more than one disconnecting means, it must be clearly marked machine's main disconnecting mean. So make sure if you have multiple disconnecting means or switches within the same machinery, you need to mark it whichever is the main disconnecting mean. Okay. And last but not least, as John mentioned earlier, arc flash and shock hazard concerns makes it more desirable to locate the supply side disconnecting means in either a separate enclosure to ensure there is no power while performing the maintenance activities around the control panel. So just keep this power compartment separate from all the control gear what is inside your panel. Let's go to the next slide. So in this slide we talk about electrical safety, which is totally in our wheelhouse here at Grace Engineered Products. This section again aligns directly with NFPA 70E standards for workplace electrical safety. So here are the changes. Language to warn against electrical hazards was removed from NFPA 79, and this section uses some new terms for basic protection and fault protection definitions. So basically, basic protection calls out any live parts operating at 50 volts AC or 60 volts DC shall be guarded against direct contact. So meaning a protection against direct contact, which is primarily shock hazard. And secondly, from indirect contact perspective, there is a fault protection like arc flash hazard, one must be protected as well. So new definitions have been added to these sections, and 6.2 and 6.4 provide some additional information within the standards for what those details are. So each machine has unique requirement, and hence it has to meet the fundamental premise of protecting the people from hazards. Though 79 is considered electrical safety document, it aligns with 70E and 70B standards for electrical safety and recommended practice for electrical equipment maintenance. So lack of proper maintenance and lack of use or misuse of PPE can often result in a hazard. Okay. So the next one is the 5314 now specifies the disconnecting means must be interlocked with the control enclosure. So meaning interlocking is key component from protection against electrical shock. Okay. So 5314 further specifies when the disconnecting means must be interlocked with the control enclosure itself. So and also further defines the types of interlocking requirements such as mechanical interlock, electrical interlock, or both to be used in different scenarios too. Let's go to the next slide. So this slide talks about the enclosure access as it's defined in NFPA 79. Most facility maintenance workers take both qualified and skilled workers perform fine tune-ups on their machinery to optimize the process parameters, right? With just accessing the control panel. What if the enclosure doesn't have a disconnecting means? Well, they need to meet one of the criteria outlined below, okay? The use of a key or tool shall be required to open the enclosure. So if you meet this requirement, you can open the panel access without this disconnecting means. Next question is, will an access to just a key or a tool make a person qualified enough with electrical work? Okay, let's look at the second one. B states live parts are separately enclosed and guarded such that there is no contact. Okay, so if the live parts are guarded against the control components, somebody is opening the panel, so they can do it. Okay. The next question here is every panel designed to have an isolated power compartment. So these are the things that one needs to consider while designing the industrial control panels. So the next one is the big one. Worker qualification makes a bigger discussion here. Can we assume an automation engineer or a programmer to be a qualified electrical worker while programming a PLC inside a control panel? And the next question is, what in case if a skilled machine operator who is working on that machine is making some process settings change while opening the panel door? I'm sure we all have seen that before, okay? The industrial control panel shown to your right has a small door-mounted device within the red circle. So this is one of our Grace port, we call a programming port, which has been trusted over 2 decades for through-door safety by major industrial OEMs and also the Fortune 500 industrial customers as well. So please make sure that you take the exit survey after the webinar and let us know if you'd like to have a Grace port as a product sample for free, okay? Let's go to the next slide. This slide talks about the receptacles for accessory equipment as defined in NFPA 79, Chapter 15.1.1. In NFPA 79 context, we need to understand the differences between associated equipment and accessory equipment. So associated equipment is required for normal operation, while accessory equipment is not required for normal operation. That's a simple definition. Accessory equipment may be needed for maintenance, testing, calibration, or troubleshooting, and other maintenance-related activities. So basically, if you're performing programming change, you may want to use an accessory receptacle outside your cabinet, as what is shown on this slide, okay? And next thing is, receptacles used in the machineries cannot be rated for more than 125 volts AC. And only 2 receptacle configurations are allowed to be used per NFPA 79. One is a 15 amps, another one is a 20 amps, okay? Also, the receptacle must meet the environmental rating of the enclosure for listing and labeling requirements of the panel itself, okay? Given the nature of the industrial machinery, the type of operating environments, and also taking the personal interaction with the panel, any receptacle intended for maintenance personnel must have a GFCI protection per NFPA 79, period. You may ask, why I even have a receptacle to start with on my industrial control panel in first place? Well, I'm sure you don't want to be the one reporting an injury or a fatality due to the electric shock or arc flash incident at your facility, okay? So what is shown on the screen on your right is our Grace port with 2 GFCIs, Ethernet, and a circuit breaker option. We have one more GFCI inside, which makes it total 3 GFCIs in a single assembly, okay? By the way, our owner Phil Allen has this buy 2 get 1 free GFCI offer going on for more than 20 years, okay? Not only that, we can further customize our Grace port to your unique need. We have over 300 components and several power options you can choose from, including your own customized logo. All the programming ports comes with a UL recognized label, and they will be delivered in 2 to 3 business days max, okay? Enough commercial. Let's go to the next slide. So in summary, unlike other electrical equipment, industrial control panels pose a higher risk of electrical hazards, primarily due to 2 reasons. One, various voltage levels inside the panel. For example, a person may be trained on a low voltage system up to 1000 volts. If the panel has a variable frequency drive which is rated for 4160 volts, he or she may be exposed to that higher risk without intention, okay? The second scenario is if a programming engineer or an automation engineer is opening a panel to access a 24 volts DC circuit or making a change to a PLC, he or she may be exposed to an adjacent system of higher voltage and may get accidental contact with the source voltage as well. Okay, as John mentioned, we all get complacent with our day-to-day tasks, and repertoire makes workers less attentive at times. So lastly, always verify the de-energized state before opening the panel, and use safety by design controls such as engineering controls like a Grace port or other voltage indicating devices to minimize the risk of exposure from outside the door. And lastly, use the appropriate PPE as per your facility's guidelines. With that, let's go to the next slide. Hey guys, before we take the questions, I just want to make an announcement. We have an interesting webinar coming up in March This is on the topic of NEC Article 430, which focuses on motors, motor circuits, and controllers. It's a two-part series. The first webinar is on 19th and the second one is on 21st. So it's basically two different sessions. So mark your calendars and stay tuned for the registration invite, which will be coming soon. With that, we'll go to the next slide and take the questions.